In this section, I'm going to be introducing sampling and interpolation. The processes of sampling and interpolation play a crucial role in most real-world systems. As it turns out, these processes are often best understood in terms of the Fourier transform and frequency spectra of signals. For this reason, the Fourier transform is often used to study sampling and interpolation. In what follows, we'll consider this application of the Fourier transform in some detail. Often we want to be able to transform a continuous time signal, in other words a function, into a discrete time signal, in other words a sequence, and vice versa. This is accomplished through operations known as sampling and interpolation. These operations are of fundamental importance as they establish a link between the analog and digital worlds. First, let's consider sampling. Sampling transforms a continuous time signal, in other words a function, into a discrete time signal, in other words a sequence. This operation is performed by what is known as a continuous time to discrete time converter. Such a converter is shown in this figure here, where the input to the converter x is a function and the output of the converter y is a sequence. Next, let's consider interpolation. Interpolation transforms a discrete time signal, in other words a sequence, into a continuous time signal, in other words a function. This operation is performed by what is known as a discrete time to continuous time converter. Such a converter is shown in this figure here, where the input to the converter y is a sequence and the output of the converter x is a function. Note that unless very special conditions are met, the sampling process loses information. That is, sampling is not invertible. In other words, if we sample a function and then interpolate the resulting sequence, the function that we obtain from interpolation will usually differ, possibly very significantly, from the function that we originally sampled. Because of this issue, great care must be exercised when performing sampling in order to ensure that sampling does not result in significant information loss. Sampling can be performed in many different ways. In practice, however, the most common form of sampling is periodic sampling. With periodic sampling, a sequence is constructed from a function by evaluating the function at equally spaced points and using the resulting function values to form a sequence. Mathematically, we can describe periodic sampling in terms of an equation of this particular form here, where x is the function to be sampled, y is the sequence produced by the sampling process, and capital T is a strictly positive real constant. As a matter of terminology, capital T is referred to as the sampling period, and the quantity 2 pi over capital T is referred to as the sampling frequency. Lastly, on this slide, we have an example of periodic sampling. In the figure in the bottom left is a function x, which is our function to be sampled, and we're going to sample this function with a sampling period of 10. And when we do this, we obtain the sequence y, which is shown in the graph on the bottom right. At this point, I'd like to further comment on the invertibility of sampling. Generally speaking, unless constraints are placed on the functions being sampled, the sampling process is not invertible. In other words, the sampling process has the potential to lose information, so that a function cannot be uniquely determined from the sequence obtained when the function was sampled. Consider, for example, the functions x1 and x2 given by these particular formulas here. Suppose that we sample x1 and x2 with a sampling period of 1. When we sample x1 with a sampling period of 1, this yields the sequence y1, which is equal to 0 everywhere. When we sample the function x2, this yields the sequence y2, which is also equal to 0 everywhere. This sequence is 0 everywhere simply because sine of 2 pi n is equal to 0 for all integer n. So although x1 and x2 are distinct, in other words they're different functions, the sequences y1 and y2 are identical. And this leads to the following dilemma. Suppose we're given the sequence y, where y is equal to y1, or equivalently y is equal to y2 since y1 and y2 are equal. It's impossible to determine which function was sampled to produce the sequence y. Because y is equal to y1, the function that was sampled might have been x1, because when x1 is sampled, this produces the sequence y1. But because y is also equal to y2, it might have been that we sampled the function x2, because the function x2 leads to the sequence y2 when it's sampled. So essentially we have this ambiguity that we don't know whether we sampled the function x1 or x2 or possibly some other function. And it's precisely this kind of problem that leads to sampling not being invertible. As it turns out, the only way that we can ensure that a function can always be unambiguously determined from its samples is to constrain the functions being sampled in some way. At this point, I'd like to make a few additional remarks related to sampling and the potential for information loss resulting from sampling due to it not being invertible. In real-world systems, sampling is used pervasively. In practice, however, when sampling is used, it normally needs to be used in a manner that does not result in information loss. This motivates an interest in finding a set of constraints that can be imposed on sampling that would ensure that information loss does not occur when sampling is performed. Any such set of constraints, however, would have to be reasonably easy to satisfy in real-world applications in order to allow useful systems employing sampling to be developed without too much difficulty. In some of the material to come, we will analyze sampling with the help of the Fourier transform in order to gain more insight into sampling and understand how information loss can be avoided when performing sampling. Ultimately, this will lead us to a result of fundamental importance known as the sampling theorem, which offers a very practical way to avoid information loss during sampling. At this point, I'd like to introduce a simple mathematical model that we can use to study sampling and gain deeper insight into its behavior. Before proceeding, however, I first need to introduce the notion of an impulse train. In this regard, we have the definition at the top of the slide. An impulse train is simply a function of this particular form here, where the ck and capital T are real constants. In other words, an impulse train is a function that consists of a series of equally spaced impulses that are each scaled by a constant. With this definition in place, I can now introduce the simple mathematical model that we'll use for sampling. A block diagram for the system associated with our model for sampling is shown in the figure in the middle of the slide, so in this figure here. In this model, we'll denote the sampling period as capital T and the sampling frequency as omega s. The input of the system, which is denoted as x, corresponds to the function to be sampled, and the output of the system, which is denoted as y, corresponds to the sequence produced by the sampling process. The function p, which internally appears as a signal inside the system, is a periodic impulse train with period capital T. The system that performs sampling in this model consists of two main processing steps. The first step is the step corresponding to this multiplier here, and the second step is the step corresponding to this block that's labeled convert from impulse train to sequence. So in the first step, what we're doing is we're multiplying the function x to be sampled by a periodic impulse train p, which yields the impulse train denoted by s, which is given by this formula here. In other words, we have an impulse train where the weights in the impulse train are given by the function x sampled at equally spaced points, which are spaced by capital T. Then in the second step, we're converting the impulse train s to a sequence y by forming y from the weights of successive impulses in s. In other words, we're taking these weights that appear in the formula for s, in other words, the weights in the impulse train, and we're extracting them and using them to form the sequence y. This slide shows in graphical form the signals obtained at various points in the system that we're using to model the sampling process. The figure in the top left shows a graph of the input x to the sampling process. The figure in the top right shows the periodic impulse train p that is multiplied by x to produce the impulse sampled function s. The figure in the bottom left shows a graph of the impulse sampled function s, which is an impulse train where the weights appearing in the impulse train correspond to the values of the function x evaluated at points that are equally spaced by capital T. The figure in the bottom right shows a graph of the sequence y generated as the output of the sampling process, where the elements in the sequence correspond to weights appearing in the impulse train S. Although the graphs for the impulse sampled function S, shown in the bottom left, and the output sequence y, shown in the bottom right, look very similar visually, it's important to understand that they're completely different entities mathematically. The former is a function that is zero between the sample points, in other words, points that are at integer multiples of capital T, whereas the latter is a sequence that is only defined at integer points. In our analysis of sampling, one of our goals is to better understand what causes information loss when sampling is performed. In other words, what causes sampling to fail to be invertible. Our model of sampling consists of only two steps. Since the overall process of sampling is known not to be invertible, this implies that at least one of these two steps must not be invertible. So let's consider more carefully each of these steps to see if they pose any problems with respect to invertibility. To begin, let's consider the first step in our model of sampling. In other words, let's consider this particular step here. In this step, we're multiplying the function x to be sampled by the periodic impulse train p. Now consider the following. Can we undo the effect of this multiplication? Clearly the answer to this question is no. The function p is zero between sample points, and we cannot undo the effect of multiplying by zero. Therefore, the first step in our model of sampling is problematic with respect to the invertibility of sampling. Now let's consider the second step in our model of sampling. In other words, let's consider this step here. In this step, we're simply taking the weights of impulses in an impulse train and using them to construct a sequence y. Clearly, we can undo the effects of this operation. In other words, if we're given this sequence y, we can easily construct the impulse train S by simply taking the elements of this sequence and substituting them for the weights in the impulse train. Therefore, the second step in our model of sampling is always invertible. So overall, of these two steps in our model of sampling, only the first step can potentially lose information. For this reason, we want to focus our attention on this particular step and see if we can find some practical constraints that we can impose on sampling in order to ensure that it does not result in information loss. Unfortunately, it's not at all obvious how we might accomplish this based on our preceding analysis of the sampling model in the time domain. This being the case, we turn to the Fourier transform for help. In other words, we choose to analyze the first step in our model of sampling in the frequency domain in order to see if we can gain any additional insight into how we can resolve this problem of information loss during sampling. Again, I'd like to consider the system that we're using to model sampling, as shown in the block diagram at the top of this slide. In particular, I'd like to focus attention on the processing step associated with the multiplier in this system. In other words, this multiplier here. This processing step multiplies the input little x, which is a function to be sampled, by the periodic impulse train little p, to yield the impulse train little s. The operation performed by this processing step is commonly referred to as impulse sampling. Now I'd like to consider the characterization of impulse sampling in the frequency domain. In the time domain, impulse sampling is characterized by this equation here, where capital T denotes the sampling period. Expressing this equation in the frequency domain by taking the Fourier transform, we obtain this next equation here, where big X and big S denote the Fourier transforms of little x and little s respectively, and omega s denotes the sampling frequency. From this equation, we can see the effect that impulse sampling has on the frequency spectrum of the signal that is sampled. The kth term in the summation on the right-hand side of the equation corresponds to big X shifted by k omega s. Since the summation is taken over all integer k, the summation result corresponds to a periodic function with period omega s. Thus, big S is a periodic function with period omega s. In essence, the spectrum of the impulse sampled function little s is a scaled sum of an infinite number of shifted copies of the spectrum of the original function little x. At this point, I'd like to consider an example in which we show the frequency domain characterization of impulse sampling, as stated on this slide, is in fact correct. In this example, we are given an equation that characterizes impulse sampling in the time domain. In other words, we're given this particular equation here. In other words, the equation highlighted in green. And we're asked to find the corresponding equation in the frequency domain. To solve this problem, we essentially need to take the Fourier transform of a product of two functions, namely little p and little x. There are at least two different ways that we can do this. One way would be to use the multiplication property of the Fourier transform. This, however, is not a very desirable approach, as using the multiplication property of the Fourier transform will drag convolution into our work. A better way would be to proceed as follows. First, we observe that we are not multiplying two completely arbitrary functions in the given equation. Although the function little x is arbitrary, the function little p is not. We know exactly what the function little p is. Furthermore, little p is periodic, so it can be represented in terms of a Fourier series. If we represent little p in terms of a Fourier series, we can then use the modulation property of the Fourier transform in order to very easily take the Fourier transform of the given equation. Since this would avoid any need for convolution, we will proceed by this approach. Again, since the function little p is periodic, it has a Fourier series representation. So let's proceed to find this Fourier series representation. Recall that the function little p is given by this particular equation here, and clearly the function little p is periodic with period capital T, and therefore it has frequency omega s, which is given by 2 pi over t. Now, since the function p is periodic, it has a Fourier series, so we can write a Fourier series representation for this function, which is this equation here. And the way we compute these Fourier series coefficients denoted by ck is using the Fourier series analysis equation, which is this equation here. Now here we've chosen to integrate from minus capital T over 2 to capital T over 2. So if we look at the plot of little p in the top left here, over the range minus capital T over 2, which is approximately here on the axis, to capital T over 2, which is approximately here on the axis, the function that we see is the delta function. So what we can substitute for p of t is simply delta of t. Next, we can observe that the integrand, in this particular integral here, is 0 everywhere outside of the range that we're integrating, from minus capital T over 2 to capital T over 2. Therefore, we can change these limits of integration to minus infinity and plus infinity. Now what we have on this line is an integral of the form of the sifting property. So using the sifting property, this integral just evaluates to 1, and we're left with 1 over t times 1, which is just 1 over t. And of course, by definition, this is also equal to omega s over 2 pi. So it turns out all the Fourier series coefficients are equal. In other words, ck is the same for all values of k. In particular, it's equal to omega s over 2 pi. So we can then take this quantity here and substitute it in for the Fourier series coefficients in this equation above, equation 1, and this gives us this last line down here, which is our Fourier series representation of the function little p. Now, having found the Fourier series representation of little p, we return to the main problem, which is to find the Fourier transform of equation 1, in other words, this equation here. So we just finished finding the Fourier series representation of little p, which is this particular Fourier series representation here. And what we can do is we can take this Fourier series representation for p and substitute this into equation 1 for p. And when we do this, this gives us this next equation here. Next, we want to take the Fourier transform of this equation. To do this, we can use the modulation property of the Fourier transform. So in what follows, let big X and big S denote the Fourier transforms of little x and little s respectively. Taking the Fourier transform of this equation, we observe that we have multiplication by a complex sinusoid, where the frequency of the complex sinusoid is k omega s, So the effect that multiplying by this complex sinusoid will have on the Fourier transform is it will shift it by k omega s. So here we have our formula for big S, which is what we were asked to find in this problem. Earlier we studied the impulse sampling step in our model of sampling. Recall that this step multiplies the function being sampled by a periodic impulse train. We also saw that this step is not invertible. Furthermore, we analyzed impulse sampling in the frequency domain and saw that it's characterized by this particular equation here, where big X is the spectrum of the function being impulse sampled, big S is the spectrum of the function that is produced by impulse sampling, and omega S is the sampling frequency. From this equation we can see that big S is a scaled sum of an infinite number of shifted copies of big X. Two distinct behaviors can result in the summation in the formula for big S, depending on omega S and the bandwidth of the function whose Fourier transform is big X. In particular, the non-zero portions of the different shifted copies of big X can either overlap or not overlap. First, let's consider the case where no overlap occurs. In this case, only the k equals 0 term contributes to the sum over the frequency range minus omega s over 2 to omega s over 2. Therefore, big S and big X are equal up to a scale factor over this frequency range. So big X can be unambiguously determined from big S by simply applying a low-pass filter to big S with a cutoff frequency of omega s over 2. Thus, impulse sampling does not lose any information in this case. Next, let's consider the case where overlap occurs. In this case, additional terms beyond the k equals 0 term contribute to the sum over the frequency range minus omega s over 2 to omega s over 2. As a result, big S will not be identical to big X over all of this frequency range, so big X cannot be determined from big S. Thus, impulse sampling loses information in this case. The effect that occurs in this case, which leads to impulse sampling losing information, is called aliasing. In short, when aliasing occurs, impulse sampling loses information. Therefore, if we don't wish for information to be lost by impulse sampling, we must ensure that aliasing does not occur. On this slide, we have an example to illustrate aliasing in the process of impulse sampling. Suppose that the spectrum big X of the function to be impulse sampled is as shown in the figure at the top of the slide. So in other words, suppose that the spectrum looks like what's shown here. Impulse sampling results in a scaled sum big S of an infinite number of shifted copies of the spectrum big X. Again, two different behaviors can be exhibited by impulse sampling depending on omega S and the bandwidth of the function whose spectrum is big X. The shifted copies of the spectrum can either overlap or not overlap. First, let's consider the case where the non-zero portions of different shifted copies of the spectrum big X do not overlap. This is the non-aliasing case. In this case, we obtain a spectrum big S like that shown in the middle figure, in other words, this figure here. Here, the original spectrum big X is clearly visible up to a scale factor in the frequency range minus omega m to omega m, in other words, this frequency range here. So by using a low-pass filter with a passband gain of capital T, we can eliminate the extra shifted copies of the spectrum big X and scale the one remaining copy so that it matches big X exactly. In this situation, impulse sampling does not lose information, since it is possible to determine big X from big S. Next, let's consider the case where the non-zero portions of different shifted copies of the spectrum big X do overlap. This is the aliasing case. In this case, we obtain a spectrum big S like that shown in the bottom figure, in other words, what's shown in this figure here. Here, adjacent shifted copies of the spectrum big X partially overlap, so when the copies are summed, the resulting spectrum big S is distorted in the regions where overlap occurs. For example, the original spectrum big X is no longer discernible in big S in the frequency range minus omega m to omega m. So minus omega m is this point here, and omega m is this point here. Consider, for example, the interval from omega s minus omega m, so this point here, to omega m, this point here. Here we have two adjacent copies of the spectrum. One copy of the spectrum, which is this triangular shaped pulse that I'm tracing out here, which is plotted in a dotted line. And we also have this copy of the spectrum here, which I'm tracing out, which is plotted as a dotted line. Now between omega s minus omega m, this point here, and omega m, both of these copies of the spectrum are non-zero. So both of them contribute to the sum, and you can see that they sum together to distort the overall shape of the spectrum. You get this horizontal component to the spectrum here in the graph. And this doesn't resemble what we have in the original spectrum. Since it's not possible to determine big X from big S, impulse sampling loses information in this case. Lastly, observe that the condition of no overlap is equivalent to this point at omega m being to the left of this point at omega s minus omega m. Mathematically, this is the condition omega m is less than omega s minus omega m, which is equivalent to this condition here, omega s is greater than 2 omega m. So aliasing does not occur if this particular condition is satisfied, otherwise aliasing occurs. The condition of no aliasing essentially says that the sampling frequency must exceed twice the highest frequency component in the function being impulse sampled. So as long as a function is band limited and impulse sampled at a sufficiently high frequency, we can recover the function from its impulse sampled version. As we saw earlier, as long as aliasing does not occur during sampling, we can recover the function that was sampled from its sequence of samples by using interpolation. At this point, I'd like to formally introduce the specific interpolation process that can be used to recover a function from its samples, which is known as band-limited interpolation. A block diagram for the system that performs band-limited interpolation is shown in the figure on this slide. In other words, in this figure here. In this model, we'll denote the sampling period as capital T. The input of the system, which is denoted as y, corresponds to a sequence produced by sampling. The output of the system, which is denoted by x hat, corresponds to the function from which samples in y originated, assuming that aliasing did not occur during sampling. The system that performs interpolation consists of two main processing steps. The first step is associated with the block labeled convert from sequence to impulse train. The second step is associated with the block labeled H, which is an LTI system with impulse response H, where H is given by this particular formula here. This impulse response corresponds to a low-pass filter with a cutoff frequency of omega s over 2 and a passband gain of capital T. In the first step, we convert the sequence Y to the impulse train S by using the samples in Y as the weights of successive impulses in S. In other words, we use this sequence here, in other words Y, to generate these weights in the impulse train. In the second step, we convolve S with H to form the output x hat. This filtering operation eliminates the extra copies of the originally sampled function spectrum present in the spectrum of S. The results of the preceding slides can be combined and formalized to yield the fundamentally important mathematical result known as the sampling theorem. This theorem is given at the top of the slide and reads as follows. Let little x be a function with the Fourier transform big X, and suppose that little x is band limited to frequencies in the range minus omega m to plus omega m. Then little x is uniquely determined by its samples, given by periodically sampling little x with sampling period capital T, provided this particular condition is satisfied, where omega s is the sampling frequency. In other words, it's just 2 pi over capital T. This particular condition is referred to as the Nyquist condition, and if this condition is satisfied, we can recover little x from the sequence little y using this formula here, or equivalently using the second formula here, which is expressed in terms of omega s rather than in terms of capital T. As a matter of terminology, we refer to omega s over 2 as the Nyquist frequency, and 2 times omega m as the Nyquist rate. The importance of the sampling theorem cannot possibly be overstated. Many real-world systems employ periodic sampling, especially systems that are based on digital electronics. Such systems depend critically on the sampling theorem for their correct operation. At this point, I'd like to consider an example that makes use of the sampling theorem, and in particular, I'd like to consider example 6.41. In this example, we're given a function little x that corresponds to an audio signal with the Fourier transform big X. And we're told that little x is band limited to frequencies in the range plus and minus 44,100 pi. This is in radian measure, which is equivalent to 22.05 kilohertz. And what we're asked to do in this example is we're asked to determine the largest period, capital T, with which little x can be sampled such that little x can be recovered from its samples. The basic approach to take in solving this problem is to use the sampling theorem. So in the problem statement, we're told that little x is band limited to frequencies in the range minus omega m to plus omega m, where omega m is 44,100 pi. So by the sampling theorem, we have to sample at least 2 times omega m. So if we substitute in the value for omega m here and multiply by 2, we get 88,200 pi, which by the way is 44.1 kilohertz. Now in this example, we're asked to find the sampling period, not the sampling frequency. So the sampling period is given by 2 pi over omega s, so we can substitute in the value of omega s that we computed above, and this gives us 1 over 44,100. The frequency of 44.1 kilohertz that appears in our solution to the above problem has a special significance in audio processing. In particular, this is the rate at which CD quality audio is sampled. A typical setup for audio capture might look something like what is shown in the diagram added in the annotations, in other words, this diagram here. The microphone is a device that measures air pressure fluctuations. Due to noise and various other effects, the microphone output will likely have a spectrum that contains some extremely high frequencies. Since the human auditory system can only sense frequencies up to about 22.05 kilohertz, we can apply a low-pass filter with a cutoff frequency of 22.05 kilohertz to the audio signal without causing any perceptible change to humans. By applying such a filter, we ensure that the audio signal is band limited to frequencies in the range minus 22.05 kilohertz to 22.05 kilohertz. This means that we can sample the audio signal at a frequency of 44.1 kilohertz and be certain that aliasing will not occur. In this way, we guarantee that sampling the audio signal does not lose any information.